Broadcasting. Welcome to the practical overview for UO2 Practical 5, Liquid-Liquid Phase Equilibria. In liquid-liquid phase equilibria, the most important knowledge you will need is to understand and use the triangular phase diagram. Triangular phase diagrams can be presented in either an equilateral triangle or right-angled triangle form. You will be introduced to both. After that, we will look at the experiment you will be conducting for Practical 5. Liquid-liquid phase equilibria is the understanding of how a solute distributes itself differently between two immiscible liquid phases. A typical system consists of three components. We will discuss the system of acetic acid, water, and butyl acetate here. When we add water and acetic acid, as they are soluble in each other, they will combine to form a single liquid phase. However, when we add butyl acetate, as water and butyl acetate are almost completely insoluble in each other, two liquid phases will be observed. But acetic acid is also soluble in butyl acetate. As such, some acetic acid will begin to be extracted by the butyl acetate. In this system, acetic acid is soluble in both liquid phases and is called the solute. In this practical, we aim to study how acetic acid distributes itself differently in the different liquid phases. Let's look at the theory for liquid-liquid equilibria. The principle for liquid-liquid extraction aims to separate the constituents of a liquid solution by contact with another insoluble liquid. The two insoluble components create the two liquid phases. The solute distributes itself differently between the two liquid phases, depending on its relative solubility in each liquid phase. We will look at this system of acetic acid, water, and butyl acetate. Acetic acid is the solute which is soluble in both liquid phases. As butyl acetate is put in contact, acetic acid distributes itself differently between the two phases depending on its relative solubility. Finally, the two phases reach an equilibrium, and the concentrations of each liquid phase is considered to be in equilibrium. So how do we know what are the equilibrium concentrations? To know that, we need to first learn how to read this ternary phase diagram. For this system here, we consider water and methyl isobutyl ketone, or MIBK for short, as the two insoluble components. Acetone is soluble in both water and MIBK. Each corner represents the pure component. Now, what if the solution is a mixture of the three components? To find out how much acetone is in the mixture, we follow this set of numbers. They are in weight percentages. To find out how much MIBK is present, we use these numbers. And for water, we use these numbers. So how do we use this? Consider point M, which represents the concentration of a solution M. What is its composition? Following the horizontal lines, which is the acetone weight percent, you see that it contains 15 weight percent acetone. Following the lines for MIBK, we see that it contains 30 weight percent MIBK. And finally, following the lines for water, it contains 55 weight percent water. So this is the composition of solution M. Note that for every solution, the total weight percent must add up to 100 weight percent. Notice that there are two regions within the diagram. Outside the solubility curve, region A, and inside region B. If a solution has a composition which lies in region A, for example point K, it means that only one liquid phase will be observed within the beaker. If a solution's composition lies within region B, for example point M, then two liquid phases will be observed. The next question then is, what are the compositions of the two liquid phases? They must be different. We introduce the tie line. The darker lines seen in region B are the tie lines. They represent equilibrium concentrations in the two liquid phases. That is, solution L will be in equilibrium with solution N. So which tie line do we use for our system? First, we indicate our initial solution composition we added into our beaker on the graph. Consider point M. We know that we will observe two liquid phases within the beaker, as point M lies within region B. The concentrations of the two liquid phases can be determined by drawing a tie line through M until it touches the curve at L and N. You can already observe that acetone is more soluble in the MIBK phase than the water phase based on the compositions. Read off the composition at L. This will become the composition of the water-rich phase. Read off the composition at N. This will be the composition of the MIBK rich phase. We can also draw the ternary phase diagram, solubility curve and tie lines on a right-angled triangle phase diagram. Here, only two components are represented on the x and y axis. Then what about the third component? Consider point M. As it lies within the solubility curve, two liquid phases will be observed in the beaker. What is the composition of M? From the x-axis, M contains 11.5 weight percent acetic acid. From the y-axis, it contains 53 weight percent of water. Thus, it contains 35.5 weight percent of butyl acetate to give a total of 100 weight percent. To find the compositions of the two liquid phases, we draw a tie line through M and identify the points representing the compositions of the two liquid phases. Read off the compositions of the two liquid phases from the ends of the tie lines. Let's let's look at the experiment we will do today. In this experiment, we will use acetic acid as the solute. The other components of water and butyl acetate are insoluble in each other. Part A, we will prepare 4 conical flasks and add the respective amounts of acetic acid, water and butyl acetate in each flask. Note that for the compositions given, we should observe 2 liquid layers in all the 4 flasks. Shake each flask well, cover, and leave to stand for 20 minutes to attain equilibrium. Finally, we will determine the compositions of acetic acid in each liquid layer in each flask. This will allow us to draw one tie line for each flask. After 20 minutes, transfer the contents of the first flask into the separating funnel. Allow to stand for 2 minutes and separate each liquid phase into a separate beaker. Record the necessary readings for each liquid phase. Take a 2 ml sample from one phase and titrate using 0.5 m sodium hydroxide. Repeat the titration with a sample from the other liquid phase. The titration is done to determine the concentration of acetic acid in each phase. It is a neutralization reaction between sodium hydroxide and the acetic acid. This is done for the contents of all the 4 flasks. Part B will enable you to plot the solubility curve. First, we add the different amounts of water and butyl acetate into a conical flask. As they are insoluble, 2 liquid phases will be observed. Add methyl red indicator to observe the 2 phases more clearly. Now, using a burette, add acetic acid into your flask. Continue adding acetic acid until the solution in the flask becomes clear. That is, it has changed from a 2-phase solution to 1 phase. Repeat this for all the 8 amounts indicated in your lab report. From part A, when the concentration of acetic acid in the 2 liquid phases within 1 flask is known, these 2 points are plotted on the graph and connected to draw the tie line. From each flask, we will be able to draw one tie line. That is, a total of 4 tie lines will be drawn. Note that you will need to have drawn the solubility curve from part B before plotting the lines here. For part B, you would have obtained 8 data points to plot the solubility curve. This is the solubility curve you will draw. Let's review the learning points from this practical. We looked at the 2 types of ternary phase diagrams to understand liquid-liquid phase equilibrium. We say that the solubility curve separates the regions where 2 phases or 1 phase will be observed. The tie lines connect the compositions which are in equilibrium. From the tie lines, we can observe in which phase is the solute more soluble. That's all for Practical 5 overview.